Good morning, everyone. Can you hear me, those listening online? Okay. My name is Bernard Izawekai. I'm one of the research operations engineers in MINDOT. My duty today is to introduce somebody with a very flowery and rich bio. And his name is Gerard Moulzolf. He's the Vice President of American Engineering Testing, and he heads the Petrographic Division. Now, I saw a presentation in the last TRB conference, and I requested that this should be presented in our research phase. That's why we have it today. Gerard is so popular that he was featured on Channel 6, Discovery Channel, in the episode of The Lost Gold of World War II. So that you can easily watch that online. Very rich documentary you will find there. So he was featured there. Gerard has a lot of experience as a petrographer and as a scientist and geologist. Like I said, he's a geologist, a registered geologist in the states of Minnesota and a couple other states. He has been very active with the American Concrete Paving Association, the American Institute for Professional Geologists, the Aggregate Ready Mix Association of Minnesota, Concrete Paving Association of Minnesota, and International Cement Microscopy Association. Now, Gerard obtained his bachelor's degree from the University of Minnesota Duluth and became licensed in the various states I just talked about. And he's a director of ASTM C9, which is the Concrete and Aggregates Unit. And he's currently secretary of Committee 9.20, that's the Institute, and a member of ACI Committee 201. He's also past president and of the former Iowa Minnesota chapter of ACI, that's American Concrete Institute. And he's currently active in many other concrete-related groups. His experience of over 28 years includes petrographic work in nearly 10,000 projects throughout the United States and foreign countries. Now, I will just tell you something. If you Google Petronite, the first name that will pop up is Gerard Moulzolf. The second name that will pop up is Gerard Moulzolf. That's we know him as an international expert in that area. And his expertise also covers aggregate silica reactivity and corrosion of steel reinforcement and pre-store cycles. So join me to welcome Gerard Moulzolf to make his presentation on the observations, the petrographic observations that they made on a 128-year-old concrete in Bellefontaine, Ohio. Gerard?
Thank you, Bernard. Appreciate that. I'm going to speak today about Bellefontaine and the 125-year-old concrete pavement that's still in existence there. And I actually had the opportunity to look at it. I had some litigation I was doing for a client in Lima, Ohio, and I flew into Columbus, and Bellefontaine just happened to be right between there and the litigation I was involved in. So I got to stop in and walk around and look at the pavement. So and the statue of the originator and the inventor of the concrete pavement and the first pavement placed in the United States was, and here's a picture of it, so George Bartholomew, that's the statue there. I believe that was dedicated at in 90, it was either 96, excuse me, 91 at the 100th anniversary or 16 at the 125th. I'm unsure at that, but
Gerard?
Yes.
This is Bob. We're still looking at slide one here.
Okay, I've got you. Well, I'm on slide 2. What? That's. I'm hoping that pops up.
Me too.
Let's see. Nothing yet.
Nope, still 3-1.
Well, what do you see now?
I can see your cursor moving across, but I'm still on slide 1.
Okay. I've got the PowerPoint open and not presenting unless I'm somehow stuck.
Got through the presenter.
Let me know if you're starting to see anything else.
Something changed. Seeing your Skype screen now.
People are seeing. I don't want to see that preview.
Now we're seeing something. Now we're seeing
Okay.
it does that. There we go.
Is that good now?
Yeah, I think we're on slide 2 now.
Yep. Court Avenue, 1891.
Yep.
All right. Well, let me know if we're not catching up here. That would be unfortunate. So, slide 2 here, Court Avenue, 1891, oldest concrete street in America. Again, I had the opportunity to visit Belle Fountain. And Belle Fountain is actually French for beautiful fountain. I'm not exactly sure where the fountain was in 1891 or what, but that's the name of the town. It was nearby some deposits that allowed George Bartholomew to mine these deposits and produce some cement. We're going to get into that here in just a minute. Do we have the next slide up?
Yes, we do.
Okay, good. I think maybe we're rolling here now. So here's a picture from 1925, and we can see in the foreground here Main Street paved in 1891. After that success, they paved another portion in 1893. So there's a little hill on the left-hand side, and the courthouse is located there in the middle of Belle Fountain, and it's really a big square section of streets with the courthouse in the middle on this little knob, and they paved all around it. Now, the historians say that the streets of Belle Fountain were a sea of just deep mud, certainly in the spring after snow melt, and then in the fall if they have a wet fall. And the horses and the buggies and whatnot were always inundated in the mud. And the original courthouse and the buildings you see there had areas to tie up a horse. And so they were. The city was quite skeptical of concrete, and so the person again, George Bartholomew, his story is that he arrived in Ohio in 1886. Do we have that slide up?
Yes, we do.
Okay, all right. I'll stop asking now. I just want to make sure we're there. So anyways, George was from Germany, and he had spent some time in Houston or San Antonio. And he had learned the cement making process in both of those areas. And he arrived in Ohio in 1886, and he began experimenting with these native marl deposits. Now, the town of Marl, Ohio, is about 8 miles away. And in the background, you can see a very large, very old and large drag line. And so the the cement was being produced by drag lining this marl, which has a marl is a calcium carbonate rich mud. And so when we produce Portland cement nowadays, we use a source of limestone, and we use a source of silica and a source of iron as a flux to produce Portland cement. And so these native marl deposits had a fairly perfect raw ingredient list that allowed this material to be fired in a kiln and produce Portland cement, not too unlike what we see today. So he was floating around, George was floating around in Bellefontaine, and he became an employee of the Butler drugstore. And in the back of the drugstore, apparently, is where he's experimented with producing Portland cement with a gas stove and some coffee grinders. So he worked on this. He founded the Buckeye Portland Cement Company and mined this marl, again by that drag line in the background of the last slide, and he burned this material into clinker. And when we drive off moisture off of calcium carbonate and the marl, again a source of silica, source of iron, we form a new set of minerals, and we form clinker, which are essentially pellets of various different sizes, gray pellets, which you then grind in a mill down to what we know as gray Portland cement, which is in a powdered form. Now you can see in this picture here, when we have a big roller mill, we actually charge the roller mill with, nowadays we charge them with very large steel shot. Well, back then they used flint stones, and these were actually imported from Iceland, and these stones roll around with the clinker, the raw Portland cement clinker, and they form the grind down into a Portland cement, a gray powder, which we know as Portland cement, which we add water and aggregate to, and we make concrete. So how did that go home? And we're back. You guys to the Buckeye Portland cement slide?
Yep, we're good.
Okay, good. I thought we might have messed that up, but so organized 1886, Marl City. We talked about. The pit contained just the right amount of limestone and clay to produce Portland cement. So, with the first concrete pavement, there's a lot of other firsts that come with this. Now, the town was certainly skeptical of concrete. The only concrete that had been placed in the town was for a driveway for the lumber yard. And people believed that the concrete would get hammered by wagon wheels and by horse hooves and all that. They didn't have any faith in what this concrete pavement, how long this was going to last. So Bartholomew actually had to warranty the pavement. At the time, there was a $5,000 performance guarantee. By 1893, people had agreed that this was a great success, and they removed a couple sections, and they brought him to the Chicago World's Fair, where Bartholomew won an award for innovation. So they were very impressed with the material, the longevity of the material, how it was doing, and thought it was a great opportunity to show off. So, hence, with the first pavement, we have the first concrete pavement contractor, WTG Snyder. The first strip was 8 feet by 220 feet. This was the 1891 pavement that we looked at. He had done some concrete walks and it used a similar ramming process, and basically concrete mixed back then. I mean, we didn't understand about slump and all of that, and this material, as we'll see here in a little bit, had to be tamped into place because it was kind of a dry mix. It was very, very stiff, like dry oatmeal. It needed to be pounded in place by tampers, and so the first contract award in 1894 to him for a road, and thereas he became the first concrete paving contractor. Back then, Bartholomew was paying $2 a day. Just some interesting notes here with this pavement. Again, they were ridiculed that this pavement would not last, and it did. And we're still talking about it today, and it's still in place. So, first cement salesman, also christened. He was a druggist at the Butler Pharmacy, working with Bartholomew. Another interesting anecdote here. They labeled the barrels Nuremberg, which is a city in Germany. The going thought in eastern United States was that German cement was superior to United States cement, and so they just started putting Nuremberg on the barrels. This guy was literally selling barrels out of the back of his Model T or Model A or whatever it was at the time, and became the first cement salesman. So this is what the pavement looks like. This is what it looks like today. And the original pavement is the kind of mortar eroded that you can see the aggregate hanging out of it. This most extensive repair was done in about 1962, and a lot of the joints were raveling or rotting out. They did kind of surgical repairs by saw cutting out some of the old concrete and at the joints and replacing it with some newer concrete. And so that's a lot of what it looks like. When you walk the pavement today, that's a lot of what it looks like. And the samples that we're going to talk about that we analyzed came out of this 1962 repair. Some chunks were retained and saved. And so a larger portion of this pavement in the 60s was the subbase was destroyed by a water main break, and they lost a lot of pavement as they grabbed a lot of these pieces out and either recycled them or brought them to a yard. But so a lot of it was lost around in the 60s. So now, interestingly enough, some of the concrete that was saved, they took some cores out of, and we got some compressive strengths upwards of 8,000 psi, which is in line with a lot of pavement we're doing today. So getting to the analysis that we performed, we were contacted by Larry Schofield of the American Concrete Pavement Association, and this was 2 years back, 2.5 years back, and he commissioned kind of a group of laboratories to do some work and do a number of different things. So American Engineering Testing, along with Braun Intertech, did some classic optical microscopy and concrete petrography, and this is per ASTM C856. We also did some air void analysis, hardened air void analysis, which is commonplace nowadays for the quality and durability of concrete. That was also performed by AET and Braun. Carl Peterson with the University of Toronto did some scanning electron microscopy and some thin sections, which we'll see. And then we're going to briefly touch on Dr. Jason Weiss out of Oregon State University. Did some interesting, very new versions of transport and permeability testing of the concrete. So we'll just touch on that. And then there is a summary report available of all of this work, and it's available on the ACPA website, American Concrete Pavement Association, and it was written by Dr. Larry Sutter of Michigan Tech, a recognized expert in concrete pavements, and so all of this information is available, and there's a good number of articles also that's available including one by Luke and Billy Snell, formerly of Southern Illinois University, against American Concrete Institute. Has an article by them in March 2002, and some further other publications in the ACPA and ACI. So there's more information if you're hungry for more of that information. This is a sample that was retained after the 1962 rehabilitation of joints. And we conversed with Larry Sutter. We received the samples here in St. Paul at American Engineering Testing, and for saw cutting analysis. And we then saw cut some pieces out of this and another sample, this one here. And you can see this one's a lot like Swiss cheese. And a lot of these cores that were taken were for the compression testing at 8,000. That came upwards of 8,000 psi, and I believe a number of these samples were also kind of passed around and given to people around the time of the 100th anniversary. So some dignitaries had samples given to them of this great achievement in concrete durability. So you can see where we made some of the saw cuts to produce some slabs of this concrete. And if you're not familiar with concrete petrography, basically you're saw cutting and lapping at progressively finer grits. You're saw cutting and lapping sections of concrete to put under the microscope and kind of reverse engineer the concrete and document the aggregates, the paste aggregate bond, carbonation, paste hardness, any types of reactions that are going on. And you also make thin sections of the concrete, which we'll look at, microscopic thin sections, so you can actually see Portland cement and anything else that's in there and get a better look at reactions and all that. So it's classic optical microscopy, again, per ASTM C856. So we'll touch a little bit here on what makes concrete durable in severe environments. Now, a great deal of us online here in states that see a number of freeze-thaw cycles. And in order for concrete to be freeze-thaw resistant, we need to start with a low permeability. And this comes with greater age of concrete. It also comes with the use of pozzolans, slag cement, fly ash, things like that can produce lower permeability concrete. Minnesota Department of Transportation has a low water cement incentive for paving, a 0.40 water cement ratio, which produces very dense concretes, which keeps water out, keeps salts out, and allows the concrete to behave better in cyclic freeze-thaw. Secondly, an adequate air void system protects the concrete. When you entrain an air void system into the concrete, and we're talking 6 or 7% little bubbles, and they need to be fine enough and spaced close enough together to produce freeze-thaw resistant concrete. And in theory, when the concrete paste is saturated with water and a frost wave moves into the concrete, the water freezes into the void, and thereby releasing that 9% expansion of water when it freezes, relieves that pressure on the concrete. The concrete does not crack. And as the concrete freezes, capillary action and the surface tension of water pulls the water back out of the void space and into the paste, and you're ready for the next freeze-thaw cycle. Now, when concrete does not have low permeability, you get salts, brines, things that go into the concrete and allow the concrete to become more critically saturated and hold more water due to osmosis. Fresh water will then get pulled into the concrete, especially at the joints, and with the salt, and allow that concrete to become critically saturated. So when the water freezes into the void space, it may be sucking more water in there, and we get things like joint rot, joint distress, freeze thaw, distress, scaling, things like that. And so big deal to keep water out, keep salts out by producing low permeability concrete, allowing that air void system to further protect the concrete. Now, curing is the third note I've got here, and these are kind of in decreasing order of importance. Now, curing really is going to just affect the surface durability of the concrete paste. So if you have exterior flat work, sidewalks, curb and gutter, bridge decks, concrete pavement, if it's not adequately cured, you severely lessen the durability of that surface paste. By not keeping the water in there and keeping the Portland cement happy and hydrating and producing the glues that hold the concrete together and making that surface dense and hard. If you don't accomplish that curing, you will see surface degradation up to surface scaling, but generally surface paste erosion, aggregates exposed much quicker than they should, aggregate polishing and things like that. So lastly, placement, consolidation, and finishing. Finishing has a great deal to do with surface durability, working water into the surface, working up a latence or high water cement ratio surface would degrade the surface longevity. Placement and consolidation, getting a concrete consolidated, and so there's no honeycombing and all that. And we're going to look at what's very interesting about this concrete with regards to consolidation here in just a minute. And again, the placement methods nowadays, we're getting the concrete to move where we want to by using vibratory screeds on bridge decks, using spud vibrators to get concrete properly consolidated, and then the use of admixtures, water reducers, superplasticizers, and even self-consolidating placements in large beams, columns, things like that, by the use of viscosity modifying admixtures, the next generation of admixtures, VMAs, viscosity modifying admixtures. So you get the concrete to actually self-level and be fully consolidated, especially in structures that contain a lot of steel reinforcement. So, all right, after that primer here, we'll keep going. Now this is a saw cut and lapped cross section of this pavement, and this pavement was about 8 inches thick, 6 to 8 inches thick, and we can see from the top of the pavement's at the top, the bottom of the pavement's at the bottom, and we've got this lapped cross section. Now we can see right away we see a definite color change, and when a concrete petrographer first saw cuts and laps a section of concrete, we look at aggregate distribution, colors, sand distribution, paste, and all these things. And what we note right away is this very interesting layered appearance. And this is the way this concrete was placed. The first lift of this concrete was very chunky, very low, a very low slump, if you will. It was under consolidated. So there's a great number of consolidation voids. They're hard to see, but the very chunky nature of this concrete was due to the aggregates, the gap grading, and the low water. And so they tamped this material in place. We notice this upper layer that's almost 3/4 of an inch to an inch thick, an inch and a half to 2 inches thick, the centimeter scale on the side there. And we notice this is gray. It's very much more well consolidated, a higher slump. And note that the aggregate is more of a pea gravel and torpedo sand, is how it's been referred to, a very coarse sand, not unlike this looks not unlike a setting bed, mortar setting bed that's got pea gravel in it, a similar gradation to concrete block, but a much denser concrete. And we note that color change. And when we put a pH indicator down on this concrete, and it's called phenolphthalein, and we stain the concrete, we're staining the areas of the concrete this magenta coloration, and that's where the high pH is retained in the concrete. So this is dense and it is not carbonated. And carbonation is a chemical change in the concrete that if anybody's been working with concrete out there knows that concrete has, in a plastic state, coming right out of a ready-mix truck or a plant, has a very high pH. And if you work in it for quite a few hours, you can actually burn the skin off your legs or burn your skin on your hands because it's very caustic, and the pH is upwards of 12.5 or 13. Now, the areas where the high pH is retained in the concrete stains this magenta coloration when we spray phenolphthalein down, which is just this colorless material, colorless liquid, stains these areas pink. The areas that are carbonated, that are now somewhere down below a pH of 9 or down to as near as neutral pH at 7 on the pH scale, these areas are carbonated. It's lost that pH. The paste has chemically altered, and the paste is again altered somewhere near neutral pH, somewhere around not unlike limestone rock. So if this happens over many years, this concrete is actually relatively dense and hard and strong. And so it's very interesting that this carbonation, it usually happens on exposed surfaces, especially the top surfaces of exposed surfaces of concrete. And we note that this carbonation is actually on the bottom 2/3. And so this has been exposed to air for 125 years, carbon dioxide, carbon gases, and moisture, and it altered this concrete paste. And what we generally think is that carbonation occurs in most concretes at about 1 millimeter a year, or 1/32 of an inch a year. So note that the carbonation is very negligible at this top surface. And what this is telling us is that this cap, the second lift of concrete mortar on this pavement, is extremely dense and extremely impervious, and it has resisted this carbonation, this chemical change that occurs naturally in concrete, for 125 years. This is special. This is very special. So the open nature of the underconsolidated, almost honeycombed nature of this lower lift is fully carbonated. And so that's what we're seeing there. So very interesting here as we talk about the quality of this concrete and how it's been able to survive for so long. So next slide here, as we get a little closer in magnification here, we're actually under magnification, and we're using low angle light. So low angle light kind of casts some shadows. And so first thing, we've got a 7 millimeter, 6.9 millimeter depth of carbonation. And so it's ranging from negligible just to the left there, and spikes upwards of 7 millimeters along cracking. You can see kind of a crack with carbonation intermittent down along it. Just a little farther to the left, you can see that crack progressing vertically down through the concrete. We can see some areas that are carbonated. Now, another interesting thing to note here, we were talking about air entrainment and the necessity of having little bubbles well spaced throughout concrete to relieve the pressures of freeze thaw and make concrete durable in the severe freeze thaw environments of which we know our bridge decks, curb and gutter, sidewalks, pavements go through. And note all the little kind of black bubbles. And we've cast a low angle light across these, so these bubbles show as dark voids. And we see a lot of little voids throughout this concrete. Now, what we have to remember is air entrainment in concrete was not realized and not thought of as important until the 1950s with Powers. And you can look up work by Powers in the 50s on freestyle resistance of concrete with air entrainment. We did not realize this until the late 50s, where we started actually specifying concrete with an air entrainment to relieve the pressures of freezing and thawing. We made a lot of great concrete prior to the 50s that was very dense. And another thing to note, which we'll see some pictures of, is that Portland cement was very coarse back then. Nowadays we like quick strengths, high early strengths, and the Portland cement is ground very fine. Back then, certainly at the time of Bellefontaines concrete pavement, the Portland cement was ground as coarse as fine sand. And so we produced zero gaps in these concrete mixtures, from the coarse aggregate to the pea gravel to the sand to the Portland cement. These were very well graded mixtures through the Portland cement, and we made very dense concretes without even realizing it. So we have this evidence that we have low permeability. We have this anomaly where we have produced concrete that has some air entrainment in it, and we'll touch on a little bit later, but there's some speculation that some oils or some animal fats or tallow got into the production of this Portland cement just as a grinding aid, and this material ended up here, and it ended up as a surfactant, and it produced a lot of little bubbles. Now that's speculation. There is some history with that, not related to this project per se, but we've got little bubbles, and this concrete was placed 128 years ago. And so very interesting to see this, and another factor on why this concrete survived. Now we look at concrete a little farther down, and we see the aggregates I've used. Some crushed aggregates in here, some pea gravel. Here's some pea gravel. If you're seeing the cursor, we have some aggregates that were crushed. We don't know the significance of that, how much of that aggregate was crushed, how much of it was natural gravel. Some other interesting anomalies we see these darker masses, and these were just poorly mixed areas in this concrete, in these two lifts of concrete. Now, in reading from Concrete International of 2002, the mixing of concrete was done without heavy equipment. The sand, stone, and cement were dumped into a pile, and after mixing the concrete with hand-powered screw mixers, the concrete was tamped into the forms. The mixing and placing method entrapped approximately 8% air. The concrete was cured by the continuous wetting of 2 inches of sand, and so this is old school, putting wet sand down on this concrete and keeping the sand wet for 1 week. So that's from Billy and Luke Snell at 2002, their article in The Oldest Concrete Street in the United States. So hand mixed, and so we don't expect, the greatest mixing. And we got these areas that were a little bit denser and undermixed, and so all in all, they did a great job. But we can certainly find these anomalies. Here's another anomaly outlined in red of darker, denser concrete, had less air bubbles in it, and just part of the mixing process. And note that cracking up towards the top surface. There's some white secondary deposits, and there's some cracks that are very white and filled with secondary material. So very interesting there. We'll see some closer views of that. Now here's again a socket cross section under higher magnification. Note all the little bubbles. This concrete looks practically air entrained, and this could be mistaken for a very recent concrete pavement. I mean, a lot of concrete that's going in in Minnesota, Wisconsin, all through the Great Lakes, all through the frost belts of the United States, this doesn't look like that bad of an air content that is purposely entrained, either using a natural Vinsol resin or a polycarboxylate, newer synthetic air void system that we put in concrete to produce freeze thaw durability. So crude oil as fuel for the kilns to burn the clinker, burn the limestone and produce clinker, crusher oil, or tallow, again used as a grinding aid in crushing this material, and likely put a surfactant of some kind of organic material into this concrete and produced air just by sheer accident. So we look at the lower lift of this material, of this concrete pavement, and we see lots of large voids under consolidation, and again, the gap graded nature of the coarse aggregate, having some 1.5 inch aggregate in there, so 3/4 inch aggregate, and again the torpedo sand and all that, and mixing this in a very chunky nature, and then tamping it into place. And what this does not look unlike is pervious concrete pavement. And pervious concrete pavement has upwards of 15 or 20 or 25% void space. And when you pour, one of the true measures of a pervious pavement is having open base, and you can pour a 5-gallon pail of water down on this concrete and it drains to the grade. And there have been lots of experiments with pervious concrete pavement. There is a well-known placement of an entire neighborhood just north and west of Minnesota Department of Transportation offices. An entire neighborhood produced with pervious concrete that has performed admirably over, I believe, 15 or 20 years. Someone correct me if I'm wrong, but has performed great. This concrete has upwards of 8% void space, under consolidated, likely drained quite well, keeping the water out of it and increasing the longevity of this concrete and freeze thaw. Now, and the paste itself in these areas is not air entrained. There's bubbles, but really all the void space is an entrapped void or under consolidation void. So we produce some hardened air void data here. So the upper layer, we found 7.5% total air, and this is right in line with any modern concrete pavement. Entrained volume, which are void spaces that are less than 1 millimeter or 0.04 inches in diameter. Void spaces that are intersected when performing hardened air void content by ASTM C457. So 6.6%. The entrapped voids, again, greater than 1 millimeter, and a sign of consolidation voids. The spacing factor, very interesting. 0.008 inches. This is right in line with the minimum that is, or the maximum that is required for freeze thaw resistance for modern pavements. 0.008 inches or less for spacing factor. The lower under consolidated material, which is the first lift, is 7.9%, again around 8% total volume. The entrained was 4.3%, against void spaces that were intersected during hardened air content testing, and less than 1 millimeter in diameter. The entrapped, very much larger, 3.6, nearly half of that void space is entrapped volume, and some of this is much larger. Now the spacing factor is 0.012, which is just out of the range of freezing and thawing, but still offering some freeze thaw resistance. So, all right. Some other interesting petrographic anomalies that were noted in this concrete. Now, very interesting image, and we can see a lot of sub-horizontal. This is taken right at the top surface of this pavement, We're under fairly high magnification here, probably 20, 30 times magnification. Note those white secondary deposit filled subhorizontal microcracks. And you see a number of void spaces that are filled with white secondary deposits. There's been a lot of talk lately. A lot of concrete technologists are talking about self-healing concrete. Well, here's a 125-year-old pavement that is your first occurrence of self-healing concrete. It's been happening for 125 years. So we got some scaling, some incipient scaling or incipient spalling in this concrete that stayed in place long enough for the concrete to self-heal and fill these cracks with secondary calcium carbonate. The latest technology, the latest people talking about this is about producing concrete with a bacteria that produces calcium carbonate as a secondary deposit and self-heal cracks. This is what's been going on here in this pavement. And we still have, in most areas of this pavement, we still have an original surface that's seen quite a bit of mortar erosion and traffic wear, but the aggregates are staying there. But we don't see this scaling or spalling of a typical exterior flat work undergoing freezing and thawing and surface distress. This has self-healed. So very interesting petrographic anomaly here. But again, showing you a number of things that we're seeing that were very special about this pavement. When we make a thin section, which is a glass slide that has a very, very thin slice of this concrete on here. So basically what we do is we saw cut and lap another section. We epoxy impregnate it. We glue it to a glass slide. We then cut it off very thin, grind it down very much thinner, and polish it. And we put this under a polarizing light microscope or a petrographic microscope, which passes light through the thin section. Now what we see here is right in the dead center of this image is a rounded quartz sand grain. We look to its immediate center left, and that is a limestone aggregate. We can look all the way to the center right, another limestone sand particle. And then up at the top, we see this kind of granular with pastel colors. That is another limestone pea gravel particle. Now we can look and we can see we've cross-polarized the light, which has produced all of these colors. And it's a petrographer's tool into identifying aggregates, secondary deposits, and other portions of the paste. And we can get into a 5 or 10 minute dissertation on this, but it's a very diagnostic tool that geologists use and petrographers use when identifying rocks and minerals and concrete. So we can see these. We can see the bright colors and that are given off by these secondary deposits in these subhorizontal cracks. So we can see that. We can see they're filled with secondary deposits. So we can actually see void spaces filled by secondary deposits. And there's a line of 3 of them that are the center, lower central portion of the image. You'll see 3 void spaces with all kinds of kind of wispy looking, and there's some reds, yellows, and grays, secondary deposits there. So all of this paste is filled with secondary deposits. The cracks are filled with secondary deposits, and they've kind of self-healed this concrete. And these secondary deposits are of calcium hydroxide and of calcium carbonate. And so calcium carbonate is exactly what limestone is made of. And it is one of the most common secondary deposits in or around concrete. This image here that has this kind of fluorescent cast to it, this was produced by Carl Peterson at the University of Toronto. In fact, Carl was a former petrographer for Minnesota Department of Transportation a number of years ago, and a graduate at the University of Minnesota. So he went on, after he left Minnesota Department of Transportation, to be a researcher under Dr. Doug Hooton at the University of Toronto. So this is one of his images, and this is using fluorescent dyes to really highlight the cracking in the concrete, and we see this. This is the same exact image. We see that gray quartz grain right in the middle, and we see the same images. We'll go back up here. This thin section was Carl Peterson's also, and then he did the scan electron microscopy. Excuse me, not yet. This is fluorescent dyed epoxy and optical microscopy. So, now this concrete is not without problems. There is certainly this concrete is seen freeze thaw at the joints. It is seen freeze thaw of the aggregates, and the Minnesota Department of Transportation and Iowa and Ohio and just about anywhere that uses limestone aggregate or used to use limestone aggregate in their concrete has been vetting carbonate aggregates for many years. There's a certain number of carbonate aggregates that will break down after 5, 10, or 15 years. They break the concrete down because the aggregate is generally a dolomite, which is more porous than a limestone, and it is not freeze thaw resistant. And so we produce good concrete around an aggregate that is going to act like a little hydraulic ram when it fills with water and starts to break the concrete apart. And so some of these particles are in the Bellefontaine concrete, and this is one of them. So you can see the aggregate is cracking all up and acting kind of like a little hydraulic ram, and starts to break apart concrete. When all of your aggregate in concrete is made up of porous limestone, you get decracking, and which is the kind of concentric pattern cracking at joints, especially at the intersection of joints in old pavements. And Minnesota Department of Transportation, as an example, has outlawed limestone aggregate in just about all pavement, except for right down at the Iowa border, and they utilize granite, which is not going to be decracking susceptible. Some other things that people do is when, say you're in Iowa, all you have is limestone aggregate. You will do things like use smaller aggregate sizes. Not using 1.5 inch aggregate, you're going to use 3/4 inch aggregate, which lessens the danger of decracking. You fully vet each and every limestone and dolomite, dolostone bench in the state, and you certify that. So Iowa does a great job of vetting all their carbonate aggregates and try to produce the best concrete pavement they can. And so, but we see decracking in this pavement. We see certain aggregates that are blowing up. This is a problem that states were dealing with for decades and decades. A closer view of this dolostone cracking, the cracking proceeding into the paste, into the lower right hand portion of the image. There is some alkali silica reaction. Alkali silica reaction is a reaction between a susceptible aggregate that contains disordered quartz. In this case, it's chert. The alkalis in the paste, the high alkalis in the paste, the hydroxyl ions, and the alkalis such as calcium, which the whole system is flooded with. There's also potassium and a few other alkalis, and these kind of attack disordered quartz and produce a gel. The gel is hygroscopic, moisture can get to it, it's expansive, and you can produce cracking. And so we can, this is a chert aggregate particle. It's one of these larger pea gravel sized particles, and we see the gel extruding into the void. It's kind of a big, long, banana-shaped void below it. And you can see all the gel that's extruded in there. So this pavement's not immune to ASR, but there was just not that many aggregate particles, and it's not producing wholesale bulk expansion of the pavement. So a little bit of ASR, we're always going to see this. Nebraska is going to see a number of particles like this in their sand, gravel, concretes in the middle of the state. Minnesota is going to see a number of particles like this that are going to react over 20, 30, 40 years. And our shales, which would require a whole nother hour to talk about, the shales in Minnesota are going to be very quick and produce small amounts of gel like this, but do not produce bulk expansion. Another example, chert and some ASR gel. Getting to the Portland cement. This is actually a Portland cement grain from the Buckeye Cement Company, and this is, it's 3 millimeters. You're about 1/8 of an inch. That's how coarse this Portland cement. And a lot in this image, a lot of the kind of pepper. We've got kind of there's a lot of little black particles throughout the paste here. The salt and pepper look to it. A lot of those particles are Portland cement. And so you can see how coarsely ground this material is. We just didn't have the energy or technology back then to grind Portland cements fine. But, again, this concrete's made 8,000 PSI in 100 years. It's produced dense concrete, and it's a city street that sees a ton of salt, and it's still surviving. When we make a thin section and go under high magnification, this is about 400 times magnification, we start looking at this Portland cement, and it doesn't look too unlike very modern Portland cement. And so these cement grains that are, I'm going to tell you, they're very coarse, and they're outlined in blue. And the typical nature of Portland cement is clear crystals of calcium silicate, and they're generally in kind of a network or in a honeycomb look of ferrite, and the ferrite is ferric iron. It has that iron look. You can see this orange-brown look to it. That is the ferrite phase, which makes concrete gray, gives concrete its gray coloration, gives that bag of Portland cement a gray coloration. When you pass light through it, it's actually kind of an orange-brown. But that's the flux that allows you to burn and produce Portland cement and all these calcium silicate crystals, which combine with water and make calcium silicate hydrate and make the glue that holds concrete together. That's the whole, again, without getting a big dissertation here, that's the whole process of Portland cement: calcium silicates and water. And we control the set by adding gypsum to the mixture to control that set, which forms ettringite very early on. And Bernard mentioned ettringite very early on. Ettringite is a very important part of Portland cement hydration very early on, and helps with controlling set, and keeps these calcium silicate crystals from flash setting and getting that concrete to set even in your mixer. So we add sulfate to combat that and allow the sulfate to break down over 3-4 hours and allow the concrete to set. But some imagery from Dr. Carl Peterson, very neat image of the Portland cement. We see these nests of calcium silicate crystals. That is what we produce when we produce Portland cement. And again, going back to Marl, the town of Marl, the Buckeye Portland Cement Company, they just happen to have a great mixture of calcium carbonate and clays and silts that had enough iron and enough silica to produce a Portland cement. And just a quick aside, Portland cement was invented in the early 1820s by Joe Aspden, and he actually patented it in 1826. And he was a mason back in Leeds, England. And again, so that's where Portland cement came from. Nearly 70 years prior to the production of this pavement, it was discovered in England and patented in 1826. Cross-polarized light, seeing the crystals and the ferrite. Again, University of Toronto, and Carl Peterson did some scanning electron microscopy, where he actually mapped all of the various elements that are in this, if you're familiar with backscattered imagery, and using these colors starting up in the upper left-hand corner. There's the aluminum, that's your calcium aluminates. Calcium is the brightest coloration in the center image, showing you where those calcium silicates are. We move to silicate in the upper the right hand, and you see the silicates lighting up. The iron phase down in the lower left, you see where the iron of the ferrite phases light up. Magnesium, which is not all that exciting to be in concrete, we see a fair amount of that, and then we get this false color imagery in the lower left-hand side, or excuse me, right-hand side. So in the interest of time, we're going to keep moving here. Some more cement particles, a little bit more crude. There's actually some unburnt marl or limestone in here. We actually see some dolomite rhombohedrals in the center of that mass that's outlined in blue. So we can see a lot of the burning process, very crude. You would not see this in modern Portland cements, unburned materials, but they were there. So finishing up for questions and answers, the work that was done by Dr. Jason Weiss at the University of Oregon did some, see 642, which is a basic void spaces in concrete. The upper layer came up with 15.9% porosity, the lower 17.9. Resistivity very much higher in the upper layer. Again, this has to do with the non-carbonated, very dense nature of that, so much higher resistivity number versus the lower. He did some absorption work by neutron radiography, which was kind of all over the place. Again, very interesting types of work done here and procedures, but these are working much better for new concretes. This concrete being 128 years old now, versus having fresh concrete, if you will, that has high pH, and comparing it to fully carbonated concrete. Some of these procedures weren't exactly going to work out too well. The thermal gravimetric analysis, TGA, again, going to be very different because there's going to be calcium hydroxide in the upper concrete, and there's none of that left in the lower concrete because it's fully carbonated. Low temperature differential scanning calorimetry, another very interesting test that Jason Weiss is experimenting with. In this case, he was looking for calcium oxychloride, which is a destructive, kind of a ghost mineral, but a very destructive ghost mineral. And he found none of that. So that's kind of wrapping it up with those analyses. I'm open for questions, I believe. Robert and Bernard, if you were going to open the field for that, I'm ready.
Thank you, Gerard. Let's give Gerard a round of applause. That was very informative. Are there questions?
No questions online.
Any questions from the live audience? All right.
Are they able to open up a line, or?
There's a question.
I'm just curious about the state of the art. Are we still running LTs, and you've got the image analysis now to come up with spacing factors, specific surface, all that sort of stuff, and what's being done?
Well, I'll tell you what. I sit in at the committee at ASTM, the task group for C457, and they're working on precision and bias right now. Now, the latest version, ASTM C457, allows procedure C, which is the image analysis, which is where you blacken the surface, and you will then broadcast a white powder. Generally, it's wollastonite is the mineral. You broadcast a white powder into the concrete surface, and kind of scrape it and smash it into the surface, and so the white fills all the void spaces. And then you put that sample under the under a microscope and snap pictures of it for image analysis, and you got white and black. And so procedure C is there. It does work. I would say it's great for research. I know some admixture people have played with it and are doing some work with it. It's like I said, the committee for C457 at ASTM is working on precision and bias and inter and intra laboratory analyses, and we don't have that yet. I would say for us as a commercial laboratory, we don't do that. We don't do procedure C because a lot of our work is needed right away, or it's needed yesterday, as you know, with some contractors. And we perform linear traverse methods, and our petrographers do the linear traverse method. And so when they're going across 100 lineal inches, they're noting secondary deposits, ASR gel, other things as they're going along at 75x and traversing across a core. If we had to saw cut and lap another piece of core and do the image enhancement by staining it with black ink and playing with the powder and all that, it would actually slow a commercial lab down. So for research purposes, awesome. If you have 30 cylinders in your admixture company and you're doing R&D on your admixture, perfect, because you're not doing anything else. It just doesn't work for a commercial laboratory that well. So hopefully that answered that.
Well, any other question? Quickly, in the interest of time, we built a 2-lift concrete pavement in 2010 in our main road facility, and that was second to one that was built, I believe, in Kansas. And we saw that as an innovation. But you're telling us here that 128 years ago, we actually built 2-lift concrete in Bellefontaine. What do you think should be our approach to 2-lift concrete? Do you think we should look at it again economically? Because we had an opportunity to put recycled aggregate in the lower lift, and we put a richer mix in the upper lift. And we didn't see any cold joints between the upper and the lower lift. And everything worked so well. There was no flexural specimen that failed at the interface. So what do you think, how do you think we should look, very briefly, how do you think we should be looking at 2-lift concrete in terms of one of the tools in the toolbox? Or is this something we should even think about at all?
In doing the lifts, in doing 2 lifts, Bernard?
Yes.
Well, I think it's being done. I know it's being done in some commercial slabs on grade. A lot of it's been done in like some decks and but parking decks, and so they get the concrete in under the first mat, under the mat of steel, and then they can come in and put a second layer in. And a petrographer can see that, and sometimes we see this application line between the 2 placements. It's not a cold joint per se. We can call it a vague cold joint, but sometimes you see a different air content below versus the air content above, and if the concrete's been sitting there more than maybe a half an hour, you will see a rind, R-I-N-D, a rind between the 2 concretes. This process, this 2-layer process, was patented for something called a granitoid, O-I-D, but a granitoid process. And this 2-layer, where the first layer is very chunky and porous and drainable, and the upper layer is like this denser mortar. And we reversed and engineered one for the city of Duluth a number of years ago, and I think Minnesota DOT was involved in the reproduction of these granitoids in Duluth, and in producing literally kind of a precast concrete, and producing these granitoids. And so this was a patented process. It's a 2-layer process. It worked very well. We reverse engineered it, and Duluth did it out of the interest of historic continuity. Now, another thing that Minnesota DOT doesn't, well, most states don't do, but California has been playing with for quite a while, is precast concrete panels. And that would be an interesting use, Bernard, of a granitoid-like material where you've got a very dense material as the wear course, and a lighter. It's going to be lighter. It's going to be a lower mass, and producing that kind of layer. So California's doing it. There are precasters that are making precast panels, and they leave some voids at the bottom and a couple of holes for pumping in a grout. Once they're put in place, laid in place, and kind of locked together with some dowels or rebar, then they pump a grout underneath those in these channels to lock these panels in place. And so California's messing with that. Say the DOTs are doing something like this with bridge decks, whereas you're putting down a structural concrete that is several inches in thickness, and you're using ordinary aggregates, which in most cases you're using ordinary aggregates that are pit run gravels that may have a pop out or two, and then you're milling the surface, getting a nice interlocking surface for this deck, and then you're putting a couple inch wear course, which is ultra strong, and granite aggregate, and so you're kind of doing a layered effect on bridge decks nowadays too. So that is producing an economical, very high strength wear surface, and without doing 8 or 10 inches of it. You're producing 2 inches of it and using more of a ordinary concrete underneath it. So I think it's kind of being done, Bernard. Hopefully that kind of answered.
Sure, it does. Yeah, we appreciate this presentation. Very informative.